Systems today are demanding more speed than ever before. Think about data centers crunching AI models, autonomous vehicles processing all that sensor data, or even high-end workstations.
Right, the demands are just huge. And the backbone connecting the high-speed components in, well, pretty much all these systems is often PCI Express or PCIe.
And while that speed is phenomenal, it does create a real challenge. When complex systems at these speeds hit problems, finding the root cause can be incredibly difficult.
Oh, definitely. Especially those elusive transient bugs that appear, sporadically. They often laugh at traditional debug methods. It's tough.
Right. It feels like trying to find a needle in a haystack that's moving at 100 miles an hour.
Yeah.
But with PCIe 6.0, a major shift occurred, and it brought with it a clever kind of built-in solution for this exact debug dilemma.
Absolutely. PCIe 6.0 didn't just get faster. It fundamentally changed how data moves on the link with the introduction of FLIT mode. And embedded within this new mode is an innovation designed specifically to help engineers see inside NOP FLIT payloads.
And that's what we're diving into today. We're pulling insights straight from the source material you shared with us. So let's unpack what NOP FLIT payloads are, understand why they became necessary in PCIe 6.0, how they work, at a structural level.
And critically, how they provide this crucial new window into what's happening deep inside a high-speed PCI link. It really offers you a shortcut to understanding a complex piece of modern debug tech.
Okay, so to really grasp NOP FLIT payloads, we first need to understand the big picture change in PCIe 6.0. I mean, the headline is the speed, right? 64 gigatransfers per second per lane.
Yeah, 64 GTs, effectively doubling the bandwidth of PCIe 5.0. It's a massive leap.
Doubling the speed over the same single connection. How is that even possible without, ripping out all the cables?
Well, the key technology enabling that leap is PM4 signaling. That's pulse amplitude modulation with 4 levels. Instead of the simpler on or off NRZ used previously, PM4 uses 4 distinct voltage levels. So it represents 2 bits of data per symbol per clock cycle. This lets you push twice the data through the same channel in the same amount of time.
Okay, so you're squeezing more out of the pipe, basically. But doesn't PM4 mean the signal is a bit more, fragile? Bit more sensitive.
It does, yeah, that's the trade-off. A direct consequence of using PM4, especially over channels maybe designed for earlier tech, is a higher inherent bit error rate, or BER.
Because the levels are closer together.
Exactly. With 4 levels instead of 2, the voltage differences between them are smaller, so they're just more susceptible to noise and interference.
And if you have a higher error rate, you absolutely need a reliable way to fix those errors on the fly. Can't just let them go.
Precisely. That higher BER wasn't acceptable for a reliable link, obviously. So it mandated a robust error correction scheme. PCIe 6.0 introduced lightweight forward error correction, or FEC.
FEC, right.
FEC adds redundant bits to the data stream before transmission, allowing the receiver to detect and correct a certain number of errors without needing the data to be retransmitted. It's really a critical step for maintaining link integrity at 64 GTs.
And this sequence... Okay, let me see if I've got this.
Right.
The demand for speed leads to PM4.
Right.
PM4's higher error rate requires LVC.
Yeah.
And FEC needs a specific data structure to work efficiently. That's the fundamental chain that drives the change.
Right. That chain of dependencies is absolutely the core insight.
Yes.
Because FEC works most efficiently and quickly when it's applied to fixed-size blocks of data. And this is what directly led to the adoption of FEAT mode.
Because the old way didn't work.
Well, the variable length packets, the TLPs used in earlier PCIe generations, they just weren't suitable for this low-latency FEC application.
Okay, so FEAT mode it is. Tell us, what exactly is a FFST in PCI 6.0?
So, a FFLIT, or Flow Control Unit, is a fixed-size unit of 256 bytes. This is a fundamental break from the variable length TLPs of the past, as you said.
256 bytes. Fixed.
And the decision to operate in FLIT mode is actually negotiated pretty early during link training, using a specific bit in the TS1 ordered sets.
And operating in this fixed-size FLIT mode, I assume it brings benefits beyond just enabling FEC. It sounds like a big change.
Oh, yes. It's a foundational change with, cascading advantages. FLIT mode removes the old 128B, 130B encoding overhead found in previous generations.
Oh, efficiency.
Right, which boosts bandwidth efficiency, particularly for smaller data transfers. It contributes to lower transaction latency because the FEC is designed to correct errors incredibly fast. We're talking under 2 nanoseconds often.
Wow.
The fixed size also simplifies the design of the hardware logic at the physical and data link layers. Plus, there's a new TLP header format optimized for FLITs, allowing for larger 14-bit tags compared to the 10-bit tags before. It's a complete paradigm shift in how data is structured and moved across the link.
Okay, speed needs PM4, PM4 needs FEC, FEC needs FLITs. I think I've got that chain now. So how do these NOP FLIT payloads fit into this new FLT-based world? Are they just empty data slots, like placeholders?
That's a great question, and it's really crucial to make a distinction here. In standard FLIT mode, if a device doesn't have enough actual data TLPs to fill an entire 236-byte FLIT-P,
Which happens, right?
oh yeah, all the time,
Yeah.
it will pad the remaining space within that data, FLIT, with something called NOP TLP padding. So that's one type of NOP, you could say.
Okay, so that's padding inside a regular data FLIT, just filler. But NOP FLIT payloads, the things we're focusing on, are something else entirely.
Exactly. They are not padding within a data FLIT-P. NOP FLIT payloads are specific, dedicated debug FLITs. Think of them as specialized data packets defined in PCIe Gen 6 and later, used purely for conveying debug information without disrupting the primary flow of transaction data.
So they have a mission other than just carrying application data? What's a really key characteristic of their design? What makes them special?
A defining characteristic, and maybe the most important one, is that they originate and are handled right at the physical layer.
The lowest level.
Right down at the PHY. And this independence is vital. It means debug information can be generated and transmitted even if the higher layers, the data link layer or transaction layer, are experiencing severe issues. Or maybe the link itself is fundamentally unstable.
So it's like having a dedicated diagnostic lifeline within the main connection.
That's a perfect way to put it, yes. It gives you visibility even when the main data path might be broken or unreliable.
So no operation doesn't mean they do nothing. It means they don't perform a standard data operation, but they do perform a debug operation. Is that fair?
Precisely. That's exactly it. They don't carry the application-level TLPs, and they're handled completely separately from the standard data flow and its associated mechanisms like, say, flow control. And here's another absolutely critical design choice. NOP FLIT payloads are not subject to the standard ACNK handshake.
The acknowledgement for data.
Right, or the links retry mechanism for data. If an NOP FLIT is corrupted in transit, it's lost, period. It is not retransmitted. They also completely bypass standard flow control credit checks. They just go.
Okay, hold on. That's counterintuitive for a high-reliability link like PCIe. You're saying the debug information isn't guaranteed delivery. Why would you design it that way? That seems risky.
It does seem risky at first glance, but it's about the primary goal for the debug channel itself. That goal is robustness and non-intrusion, especially during link stress or failure. Think about it. If the link is unstable or failing, trying to retransmit debug data would just add more traffic.
Making things worse.
Exactly. It could even worsen the problem or get stuck in retry loops itself. So by designing them to be fire and forget dropping corrupted NOPs rather than retrying the debug channel is less likely to get jammed up.
Oh.
And it's more likely to get some debug information through, even if it's not perfect, not every single bit. The assumption is that getting any insight into the problem is better than getting no insight at all because the debug channel failed right alongside the main link.
That makes perfect sense when you put it that way. Reliability for the debug channel, not necessarily every debug packet. So why were these dedicated NOP FLITs needed? Didn't engineers have ways to debug PCIe links before 6.0?
Yes, of course. But the traditional methods faced pretty significant limitations, especially when you get to the speeds and complexities of Gen 6. You had error counters and AAR, advanced error reporting.
Wait, I've seen those.
They tell you that errors happen, sure, but they're often too summative and reactive. They don't give you real-time context about when and why in granular detail.
Just counts, basically.
Pretty much. Then there's LTSSM analysis, the link training and status state machine. Great for link training issues, but not really for problems happening during normal data transfer, in the L0 state.
Okay.
Software or register dumps can give you state, but they're often too slow, too static, and they can be intrusive, potentially changing the very timing or state you're trying to diagnose.
Right, the observer effect.
Exactly. And while protocol tracing lets you see external behavior on the wire, what TLPs went, where it doesn't give you a window into the device's internal state that led to that behavior, you see the symptom, not the cause inside.
Okay, so NOP FLITs are filling a crucial gap by providing what exactly? What's the magic ingredient?
They provide that granular real-time view into the link's internal operation. The sources point out, and I think this is key, that this is the first time debug information is exchanged on the link in such a direct, integrated way from the hardware itself.
Ah, from the hardware.
Yes. The rationale is really to overcome the blind spots of traditional methods. They let you gain insight into those hard-to-catch, transient, or timing-sensitive issues by creating this dedicated, real-time, hardware-assisted debug channel that's crucially independent of the main data flow problems.
Okay, I'm really starting to see how they fit in now. What do they actually look like on the wire? How are these NOP FLIT payloads structured? Is it complicated?
Well, there's a clearly defined structure, which is essential so tools can parse and understand them. Every NOP FLIT payload begins with a common header.
Okay.
This is a 4-byte double word, or DW, that basically identifies the FLIT as a NOP type. It's the signature.
Got it, the opening signature, like an envelope label. And after that header, what's inside?
That's followed by the NOP FLIT type payload section. And the content and structure of this section depend on the specific type of NOP FLIT being transmitted. The specification actually defines a few key types, each serving a slightly different debug purpose.
Okay, interesting. Break down the types for us. What are the flavors?
Sure. First, you have the simplest one, the NOP empty FLIT.
Empty. Sounds straightforward.
It is. Its structure is just that common header we mentioned, followed by a payload that's entirely zeros, all zeros.
Okay, and why send that?
Well, its main purpose is padding or maintaining link alignment, or sometimes just keeping a stream of NOP FLITs flowing on the link when a device doesn't have any specific debug data to send at that moment. It doesn't convey any specific debug information itself, just fills space reliably.
So a bit like that NOP TLP padding we mentioned earlier, but as a whole, distinct NOP FLIT this time. Makes sense. What's next?
Then there's the NOP Debug FLIT. Now, this is the one really designed to carry structured debug information. Its type payload section is organized into one or more debug chunks.
Debug chunks.
Okay. Each debug chunk starts with a debug chunk header. And importantly, this header uses standardized opcodes defined by PCI-SIG.
PCI-SIG, the standards body. Why is that important?
It's crucial for interoperability. It allows tools from different vendors to understand common pieces of debug data regardless of who made the specific PCIe device. Following that standard header is a vendor-defined payload.
So a mix.
Exactly. The purpose is to transmit a mix of data understood across the industry using those standardized opcodes and custom data specific to the device or vendor using the vendor payload. This is where devices can expose things like internal flow control states, buffer fill levels, error flags, maybe various performance counters. This balance is key. You get some universality, some flexibility.
That seems like a really smart design.
Yeah.
Standard parts for broad compatibility, vendor parts for unique insights. I like it. And the third type, you said there were a few.
The third main one is the NOP vendor FLIT. This type offers the maximum flexibility. Its typed payload section, immediately following the common header, is entirely vendor-defined.
No standards involved in the payload part.
Nope. There are no standardized debug chunks or PCI-SIG opcodes required within its payload area. It's a blank slate for the vendor.
And what's the use case for that?
Well, this is used for proprietary diagnostics or custom data formats that maybe don't fit the more structured NOP debug format. It's particularly useful during silicon validation, manufacturing test, or for deep dive field debug with specialized vendor tools where they need to get very specific custom telemetry out.
Okay, so NOP, MP for stream maintenance, NOP debug for a mix of standard and custom info, and NOP vendor for completely proprietary data. And knowing this structure is how the debug tools make sense of the raw bits flying by.
Exactly. Without this defined structure, they'd just be meaningless noise on the wire. The structure is what allows analyzers and verification tools to parse the FLITs, identify the type, locate the specific debug chunks or vendor data, and interpret the values within. It gives meaning to the bits.
All right, we understand the structure now. That makes sense. Let's get practical. What can you actually do with these NOP FLIT payloads out in the real world? What problems do they help you solve?
Yeah, this is where the design advantages we talked about, real-time, non-intrusive, independent, really pay off. They translate directly into some powerful, practical applications for you, the engineer, trying to debug these things.
Like getting that view inside the chip that maybe wasn't possible before, peeking behind the curtain.
Precisely. One of the most significant applications is monitoring the internal states of a device. Using NOP Debug FLITs, for example, you can pull data directly from inside buffers, queues, or internal state machines.
Wow.
You can see performance counters ticking up in real time, TLP counts, DLLP counts, internal error tallies, how full a particular buffer is getting. This exposes critical, typically opaque information that's vital for identifying bottlenecks, congestion, or just unexpected behavior inside the silicon.
So you could potentially see, say, a queue backing up in real time before it causes a visible problem on the link, like a warning light.
Exactly, like an early warning system based on internal state. And this real-time granular visibility is invaluable for diagnosing those incredibly complex link issues, especially the transient or intermittent errors that are notoriously difficult to reproduce and capture.
Oh, yeah, it only happens once a day bugs.
Those. Because NOPs can provide a continuous stream of internal state data, you can often capture the exact context around when a transient event occurs, what was happening inside right before, during, and after the glitch.
Getting that snapshot right when the problem happens must be huge for debugging those elusive issues. That context is everything.
It absolutely is. And for timing-sensitive problems, NOPs carrying timestamped internal data from different parts of the device, or maybe even across different devices in the system, can help you reconstruct the precise sequence of events leading to the failure.
Correlating events inside.
Yes. And for link instability, you can use NOPs to monitor things like the status of the retry buffer, the number of retransmissions happening, detailed flow control states, even if the main data path is struggling to stay up. It helps you move beyond just reactive error analysis towards more proactive monitoring of link health.
Okay, so you get this data stream. How do the tools you use, like protocol analyzers, actually leverage these NOPs? Does it make the tools smarter?
The debug ecosystem is critical here, you're right. Protocol analyzers are built to capture and decode the entire PCIe stream, and that includes NOP FLITs. But what's really powerful is that you can use the content of incoming NOPs as sophisticated triggers for your capture.
Trigger on the debug info itself.
Exactly. For example, you could set your analyzer to start recording all traffic only when a NOP debug FLIT indicates a specific internal error counter has exceeded some threshold you set, or maybe a buffer fill level has hit a warning point.
That sounds incredibly helpful for reducing the amount of data you have to sift through. You only capture when something interesting, defined by you, is happening internally.
It really is. It saves massive amounts of trace time and memory. And the tools, like those from Teledyne LaCroix or Keysight, allow you to correlate the internal view provided by the NOP FLIT data with the external view from the standard protocol trace.
Seeing both sides.
Yeah. Seeing, say, an internal buffer, full indication, timestamped in a NOP FLIT just moments before you observe a flow control stall or a retry storm in the main TLP trace. Well, that provides a much clearer picture for root cause analysis. It connects the internal cause with the external effect.
And that NOP vendor type you mentioned, is that mainly for the silicon developers themselves?
Primarily, yes. It gives silicon vendors the maximum flexibility for their own proprietary diagnostics needed during the incredibly complex process of silicon bring-up, manufacturing testing, and diagnosing specific deep issues in the field that might require custom telemetry not covered by the standard stuff.
So all these practical applications collectively enhance what people call observability, right? Truly giving you the ability to see what's happening inside these high-speed black boxes.
That's the perfect term for it, enhanced observability.
It's clear this feature is powerful, but its usefulness seems totally dependent on the tools and, I guess, the verification support behind it. You need ways to see it and trust it's working right.
You're exactly right. That's a crucial point. The most brilliant debug feature is useless if you can't capture, decode, and interpret the data it provides, or if you can't trust the feature itself isn't causing problems. Fortunately, the test and measurement and verification IP industries have really stepped up.
What kind of tools are essential here?
Well, high-speed protocol analyzers that support PCIe 6.0 and FLAT mode are your primary window into this world. Companies like Keysight, Teledyne LaCroix, VIVI, they all offer these tools.
And they specifically decode NOPs.
Yes. The sources mention specific features like Keysight's FLIT Viewer to examine individual FLITs and their status, including NOPs. Teledyne LaCroix's analyzers, like their Summit M616, can capture and fully decode all FLA types, including all the NOP variants. They also highlight their cross-syncet technology.
What does that do?
It helps you time correlate the logic-level protocol trace from the analyzer with the actual electrical waveform captured by an oscilloscope. So if an NOP reveals a potential physical layer issue, you can zoom right in on the electrical signal at that exact moment. It adds crucial insight.
Okay, so analyzers are key for debugging the actual hardware once it's built. What about making sure the NOP logic itself is correct before you even build the chip, in the design phase?
That's where verification IP, or VIP, plays an absolutely crucial role in pre-silicon verification. Companies like Cadence and Synopsys provide sophisticated VIP for PCIe 6.0 that includes extensive coverage specifically for NOP FLIT functionality. This is essential for simulation and formal verification during chip design.
And what does the VIP test specifically for NOP FLITs? What are they checking?
Well, they verify that your device correctly generates NOP FLITs with the right headers and structures according to the spec. They test that the receiving logic correctly identifies and parses the different NOP types in their payloads.
Including those standard opcodes.
Yes, including verifying the standardized PCI SIG opcodes within NOP. Debug FLITs are correct. They also verify operational aspects like the NOP FLIT counters working properly and stream IDs being handled right.
And what's one of the absolute most critical things the VIP has to verify about NOP FLITs? You mentioned non-intrusion earlier.
Verifying their non-interference with the main data path is absolutely paramount. Yes. The VIP must prove rigorously, through extensive testing, that sending and receiving NOP FLIT payloads has zero impact on the standard data FLIT processing. Meaning no accidental consumption of flow control credits that belong to data, no false ATK triggers based on NOPs, no interference with the data retry buffer mechanism. If your debug channel breaks your data channel, it's worse than useless. It's damaging.
That makes perfect sense.
Yeah.
The debug needs to be invisible to the main function, functionally speaking.
Yeah.
Are there any other specific verification challenges related to NOP FLITs themselves, handling them correctly?
Yes. Beyond verifying correct content and non-interference, you need to test operational aspects like counter rollovers and specific error handling for the NOP FLITs themselves. Remember we said they aren't retransmitted if corrupted.
Right, they just get dropped.
Mostly. But the specification is nuanced. If a NOP FLIT is malformed, meaning its structure is so broken it can't even be recognized as a valid NOP FLIT type.
Like the header is garbage.
Exactly, or the structure is just fundamentally wrong. In that case, the receiver should log that as a data link protocol error.
Okay, so if it's just garbled data within a valid NOP structure, you drop it silently. But if the NOP itself is structurally broken, that indicates a deeper problem with the NOP generation or framing logic on the other side, and you do flag that error.
Precisely. It's a clever balance. Accept potential data loss for corrupted NOP payloads to maintain channel availability during stress, but flag fundamental structural problems with the NOP mechanism itself because that points to a design or link issue. Verification needs to cover this specific error handling behavior thoroughly. You need tests for both corrupted but well-formed NOPs and malformed NOPs.
Okay, so zooming back out a bit, how do NOP FLIT payloads fit into the whole ecosystem of PCIe debug methods? Are they designed to replace everything else we used before?
No, not at all. That's important to stress. They are a very powerful addition to your debug toolkit, complementing the methods you already have, not replacing them.
So you still need things like the basic error counters.
Absolutely. Error counters and AER are still essential for general system health monitoring, tracking long-term reliability trends, and categorizing broad error patterns. They give you the sort of 10,000-foot view of link health. They tell you what kind of errors are frequent over time.
And LTSSM analysis for link training. Still needed.
Yes, definitely. It's indispensable for debugging link negotiation, speed, and width training issues and recovery sequences. That's its job.
And software debugging or pulling register dumps still have a place.
Still necessary, yeah. For issues related to drivers, operating system interactions, high-level application behavior, and examining static configuration states of the device, software sees the world differently.
And traditional protocol tracing of the actual data packets, the TLPs and DLLPs.
Crucial. Absolutely crucial for verifying protocol compliance end-to-end, understanding the transaction flow, and debugging the link layer handshakes, flow control, ACK SNEX on the wire. You need to see the actual data exchange.
So NOP FLIT payloads specifically address areas where these other methods are maybe less effective or have blind spots.
Precisely. They excel at providing that deep, real-time internal visibility that's just hard or impossible to get elsewhere. Information about internal buffer states, queue depth, internal counters that are completely opaque to external traces.
Things software can't see easily.
Right. We're too dynamic for software dumps, outside the scope of LTSSM, which focuses on training, and way too granular for simple error counters. They are particularly effective, as we said, for diagnosing those elusive, transient, or timing-sensitive issues that just don't leave clear traces using the older methods.
They really fill that critical gap for hardware-level, real-time insight into the internal state of the device during operation.
That's the key. They represent a shift towards embedding diagnostic capability directly into the high-speed hardware itself, enhancing observability beyond purely external views. It's designing debug in.
Well, this has been a really insightful deep dive into a very specific but clearly essential innovation in PCIe 6.0 debug. So to kind of recap the significance here, NOP FLIT payloads are a major step forward, giving you a crucial window into the internal workings of these incredibly fast links and devices.
They provide diagnostic access that just wasn't feasible before, especially when the link is operating right at its limits or experiencing complex intermittent problems. It's a new kind of visibility.
And the impact for you, the listener. Hopefully faster development cycles, more robust designs in the end, and ultimately better performance optimization because you can see what's actually happening.
Yeah, by giving engineers the ability to see deeper and react quicker to internal issues, they can iterate faster, build more reliable products, and really fine-tune performance based on actual internal operational data, not just guesswork.
Looking ahead, this need for embedded real-time debug, it isn't going to disappear as speeds increase further, is it? Seems like it'll become even more critical.
Not at all. You're absolutely right. As we look towards even higher speeds with technologies like PM4 continuing to be used in future generations like PCIe 7.0, well, the fundamental challenges that drove the need for NOP FLITs in 6.0 will persist, maybe even intensify.
So these ideas stick around.
I think the principles of embedded hardware-assisted diagnostic channels are becoming fundamental requirements for designing and debugging high-speed interfaces going forward. It's becoming table stakes.
Could we see NOP FLITs evolve further in the future? Are there ideas floating around?
It seems likely. The sources hint at potential evolutions. Maybe more standardization of PCI SIG opcodes within NOP Debug FLITs to cover an even wider range of common debug scenarios across different vendors. That would improve interoperability.
What else?
Possibly better ways to correlate NOP FLIT data across multiple devices within a complex system architecture, getting a more holistic view. Tighter integration with broader system-level diagnostic frameworks, not just PCIe specific, maybe even adaptive debug.
Adaptive debug, what's that?
Where the device could dynamically adjust the type or frequency of NOP data it transmits based on observed operational conditions. Like if it detects internal stress, it automatically starts sending more detailed NOPs.
Wow, that would be powerful. A system that can automatically tell you more about its struggles when it's actually struggling, without you having to configure it beforehand.
It would. It really would. And that leads us to a final thought for you to consider. How does embedding diagnostic channels, like these NOP FLIT payloads, directly into complex high-speed protocols fundamentally change the nature of design and debugging itself? Are we moving towards an era where systems aren't just observed passively from the outside, but are designed with the inherent capability to actively report on their own internal state and struggles in real time?
That really changes the way you'd approach building and troubleshooting these incredibly complex systems. Something to think about. Thanks for diving deep with us today.